Now what we're going to do here is we're going to do something similar to what we've done with an arithmetic sequence. We're going to look at calculating the sum to n number of terms, but this time of a geometric series. Now, we know the difference between an arithmetic and a geometric series. The one that we're focusing on at the moment is the geometric series. So that's the one that takes the format un equals ar to the n minus 1. Now, when we are calculating the sum up to a certain number of terms, the formula we're going to use for this is actually different from that of an arithmetic sequence. Remember that the general form of a geometric sequence, as we've just said, is un equals ar to the n minus 1. In this, we know that a is the initial starting term, so our u1, and r is the common ratio, which we can calculate by looking at the ratio of two consecutive terms, un plus 1 and un. Using this information and using the data from this, what we're able to do is calculate the sum of any geometric series up to a certain number of terms n using the formula Sn equals a bracket 1 minus r to the n all over 1 minus r. So this formula here. So what we're able to do is use that in our quest to calculate the sum up to a certain number of terms. Now, proving this formula works is actually relatively straightforward. Let's imagine we've got some geometric series, Sn. We know it's going to take the general format ar to the n minus 1. So that means it's going to have a term a to start with, then plus ar, then plus ar squared, all the way up to plus ar to the n minus 1. So that's what the series is going to look like. That's what our sequence of numbers is going to look like. If we then take a second sequence, but we do rs to the n, so a second set of numbers, what we do is we take this whole first sequence and multiply it by r. What we end up getting is we end up getting ar plus ar squared all the way up to then plus ar to the n minus 1, but our final term is going to be 1 power higher, so we're going to end up with plus ar to the n, because we've multiplied every single term by r, so the power of r increases by 1. If I then treat these like I would a pair of simultaneous equations, and imagine that I'm going to subtract the second sequence from the first one, go up and down, essentially like a chimney sum if you like, what I can then say is, fine, if I do Sn take away r times Sn, what that ends up giving me is a, the first term, but if you go along every single one of the terms, these two will cancel, these two will cancel, so on and so forth, up to ar to the n minus 1 cancelling, and then you're left with ar to the n. But remember, it's take away ar to the n, so that equals a take away ar to the n. If I then look at both sides of this, on this side I've got a common factor of Sn, and on this side I've got a common factor of a, so let's take those common factors out. That means I've then got Sn bracket 1 minus r equals a bracket 1 minus r to the n. If I then make Sn, i.e. the sum up to n terms, the subject of this formula, by taking 1 minus r across here, what I end up getting is that Sn, the sum to n terms of a geometric sequence, is equal to a bracket 1 minus r to the n over 1 minus r. So the formula we had a minute ago, and that's me just proving it. So I've shown you why we know it's that formula that's there. So we're able to use this when it comes to problems involving the sum to a certain number of terms for a geometric series. Best way to know this is to have a look at it in action. So let's look at a couple of examples. So let's imagine the first 8 terms of a geometric sequence whose first term is 5 and the common ratio is 1.2. We want to know the sum of that. So we want to know the sum of the first 8 terms of this geometric sequence. So what we have to remember then is we're looking for Sn equals a bracket 1 minus r to the n all over 1 minus r. Now for this formula to work, we need to know 3 things. We need to know n, we need to know a, and we need to know r. So we need to know all 3 of those to be able to accurately and effectively calculate the answer we want. Well, we know n is the number of terms, and in this case, we're told it's 8, so we know that n equals 8. We need a, which is the first term, which we're told there is 5, and we need r, the common ratio, which is told there, so it's 1.2. Once we've got all of that information there, what we're then able to do is just quite simply substitute it into the formula and calculate it out. So I can then say, fine, so my sum to 8 terms of this sequence is equal to 5, bracket 1 minus r to the n, so 1 minus 1.2 to the power of 8, all divided by 1 minus 1.2. Now this kind of question here, those types of numbers, you can just fire it into the calculator. What you'd end up getting for that one is 82.50 rounded to 4 significant figures. 82.5 to 1 decimal place, or 3 significant figures as well. That would all be totally acceptable. So there we go. If we're asked to calculate the sum up to a certain number of terms, we just have to remember we need these 3 key bits of information. We might be given the terms of the sequence and have to calculate them. That's no big deal at all. We just need all 3 of those bits of information for this one. Let's imagine then I give you a geometric sequence and it's given by 4, 6, 9, and it continues on. I want to know the smallest value of n for which Sn is greater than 200. So the sum up to that number of terms is bigger than 200. Now we did similar ones like this with arithmetic sequences as well. What we have to do is figure out the condition where our formula for the sum exceeds 200. So in this case, what we want is we want Sn, which we know is equal to a, bracket 1 minus r to the n, over 1 minus r. We want that to be greater than 200. Now from this, we know a and we know r, because we know a is the first term, which is 1, and r, our common ratio, is the ratio of 2 consecutive terms. So it would be 6 over 4, so 3 over 2. Again, we could do it from the second one. We could have 9 over 6, which again would give us 3 over 2. So my common ratio is 3 over 2, or 1.5. So what I now have to do is substitute this into here. So from that, what I need to know is I want 4 bracket 1 minus 1.5 to the n, all over 1 minus 1.5, bigger than 200. So I'm looking for a value of n that satisfies this equation here. So what I now need to do is work this through and find my value of n. So if I look at the bottom here, I get 1 take away 1.5, which gives me negative 0.5. So I've got a value here on the bottom, and I want it across here. So to do that, what I'm going to do to begin with is multiply both sides by negative 0.5. But what I'm also going to do is take the 4 times here, and I'm going to divide it by 4 on this side as well. So what that then means is I've got 1 take away 1.5 to the power of n. Now this, because I'm multiplying by a negative, remember that switches your inequality around, and I then do 200 times negative 0.5 divided by 4. So I then know is that 1 minus 1.5 to the power of n has to be less than negative 25. If I then jiggle this about, so let's say I add 1.5 to the power of n across to here, and I take the negative 25 and add it across to here just to swap sides and make the term with the n the subject of my formula, what I'd end up getting is that 1.5 to the n has to be bigger than 26. Now to solve this is when we take logarithms of both sides. So what I'd do is I'd say fine, so ln of 1.5 to the power of n has to be bigger than ln of 26. Bring the power down here, and I get n times ln of 1.5 has to be bigger than ln of 26. And then divide through by this. Remember, ln of 1.5 just gives you a numerical value. So you end up getting n has to be bigger than ln of 26 over ln 1.5. And at this point, you can just fire that all into your calculator. What that then tells me is that n has to be bigger than 8.035, and it continues on. So x has to be bigger than 8.035. Now this is where if we thought of rounding as normal, we'd round that to 8. But remember the logic behind this. If we put n equal to 8, the sum up to the 8th term would be less than 200 because it's, if you like, the 8.035th term that makes it. But we can't have a 0.35 term, we have to go up to the next one. This is where the rules of rounding go out the window and we have to punt it up the way. If you did S8 and plugged everything into this here, you would find that the value for that is less than 200. So we'd have to go to the next term, so from that, we'd then be able to say that n equals 9. So it's the 9th term, which then gives our sum exceeding 200. We have to have that in order for it to be that way. So these are just a couple of the styles of problems that we can do with geometric series and their sums to n term. There's a couple of more different ones that we can do, and you'll get a couple of examples video, but bear in mind the kind of information we need. So we always need our first term, common ratio, and the power, i.e. what number of terms we're going to go up to for us to be able to successfully work with this sort of formula.